Okay, good day. So today we will have another set of examples. Okay, so last video I have posted three different examples. Okay, so part 1, part 2, and part 3, torsion. So it's actually examples number 1, examples number 2, and examples number 3. And then in examples number 3, we have debugged, we have corrected several error in the solution so that we eventually end up with a accurate solution for the problem number 3. Okay, so here, we will have another example. Okay, so in this case we have 3.8. Okay, so we will concentrate on 3.8, problem 3.8, and figure 3.8 is its figure for this problem. Okay, so the steel shaft is formed attaching a hollow shaft to a solid shaft. Determine the maximum torque that can be applied to the ends of the shaft without exceeding the shear stress of 70 megapascals or an angle of twist of 2.5 degrees in the 3.5 meter length. Use G is equal to 83 gigapascal for steel. Okay, so this will be our question. Okay, so it is actually a composite a shaft. So it is said that this is the solid shaft and this is the hollow shaft, meaning there is a hole in between this second shaft. Okay, there is a circular hollow at the middle. Okay, so that is why it is called hollow shaft, and this is a solid shaft. Okay, so without further ado, we will introduce. Okay, I have here the solution to our problem. Okay, so here we are. Okay, so here is its original drawing. Okay, so this is a steel shaft in which the diameter of this shaft. Okay, so these are two shafts. One shaft is solid, has a 70 mm diameter, and then the second shaft is and the bigger shaft is actually a hollow shaft with outside diameter equivalent to 100 mm and inside diameter 70 mm in diameter. Okay, so they have different lengths. So the solid shaft has 1.5 meter length, and the hollow shaft is 2 meters in length respectively. Okay, so the thing that we can do is to divide this shaft into two. Okay, so in order that we can solve this problem. Okay, so this is how we divide it. Okay, so since both sides has a value of torsion which is equivalent to T. Okay, it is normally, if there is a torsion at the other side equivalent to T, so there should be a torsion also equivalent to T at the other side, so that your shaft will maintain its equilibrium. So here we divide it into two. The first one is a hollow shaft. So since this is T, so this should be also in T, so that it will be in equilibrium. Okay, and then there should be a T on the other side. If there is a T in that direction, so there will be a T on a different direction. Okay, so there should be an equilibrium. So if T, for example, here is counterclockwise, so the other side should be also T in counterclockwise, and so on. Okay, also in this problem. Okay, so please take note that in the middle there should be two equivalent torsion. Okay, value of torsion, but in opposite direction. Oh, so it's okay. So we have opposite direction of T, so that if they combine together, it will be equivalent to zero torsion at the middle. Okay. So please, we assume that the angle of twist at the hollow shaft is theta 1, and the angle of twist at the um, solid shaft is theta 2. Okay. So here is the solution. Okay. So we know that the, okay, as have mentioned in the problem, so the maximum shear stress, okay, should be 70 megapascals, and then the angle of twist should be should not exceed 2.5 degrees in the length of 3.5 meters. Okay, so we all know that, okay, the total length of this is exactly 3.5 meters. So here is the solution. Okay, so we take the maximum shearing stress as 70 megapascals, or equivalent to 70 times 10 to the power of 3 newton per meter squared. Okay, so in that case, what we do, okay, so in that case, so what we do is, okay, so we use the formula for the shear stress. Okay, so the the maximum shear stress at hollow shaft is equivalent to 16 TD over pi multiplied by big diameter, or big D to the power of 4 minus small d to the power of 4. Okay, so in this problem, the T, or the value of your torsion, we do not know. Okay, so what we do is we substitute all the uh, values which are given. Since D, okay, the big D, or the outside diameter is given, and the inner diameter is given, so we substitute. Also, okay, so that's what, okay, so that's why we get this value. Okay, so the shear stress of hollow shaft is equivalent to 6.702142623 times 10 to the negative 6 torsion. And then for solid shaft, this is the formula for shear stress of maximum shear stress of solid shaft. So 16T over pi d cube. And since for this hollow shaft, the diameter is given, so we just substitute. So we get this value, 1.484827457 times 10 to the negative 5 T. Okay, so what are we going to do? Okay, so since we have already substituted the shear stress, so here, okay, so we equate each and every one of these. Okay, so in this hollow shaft, its angle of twist should not exceed 2.5 degrees. Okay, so what am I going to do is, I equate this. Okay, so the shear stress at hollow shaft, okay, I equate this to 70 times 10 to the power of 3. Okay, so what I get is the value of our torsion is equivalent to 10,444.421 Newton mm, or 10.444 kilonewton meter. So that is its allowable torsion for hollow shaft. Okay, shear stress for hollow shaft. But somehow there will be a different value for the solid shaft. Okay, so we equate also that this formula to 70 times 10 to the 3 Newton per meter squared. Okay, so I use that value, so I have computed 4,714.352 Newton meter, or 4.714 kilonewton meter. Okay, so So there are two different values, okay? So in this problem, actually, we choose the smallest safe value for t, okay? So there will be a different values of t that we can compute, and we choose the smallest one, okay, to represent it as the safest one, okay? So we have already equated the maximum shear stress uh, with different with the portions of hollow shaft and solid shaft, okay? So these are the computed maximum allowable torsion for, this is for solid shaft, ay for hollow shaft and solid shaft. So the next one, the next thing is we need to find, okay, the allowable torsion given the criteria 2.5, it should not exceed 2.5 degrees of angle of twist, okay? So here is the here is the second part of our solution for this 3.8, okay? So we all know that if we add the theta is equivalent to theta 1 plus theta 2, should be less than 2.5 degrees, okay? So let's check in this drawing, okay? So for hollow shaft, we its angle of twist is theta 1, and for the solid shaft, the angle of twist is theta 2. So that is why we use theta 1 plus theta 2, okay? So this theta 1 is the angle of rotation or angle of twist of hollow shaft, and theta 2 is the angle of twist of solid shaft. Adding this two will result for the value of the angle of twist of the whole shaft or the whole composite shaft, okay? So here we multiply the 2.5 degrees by pi over 180 to find its value in radian, okay? So theta is equal to TL over GG hollow shaft, the theta 1, and plus TL over GJ so of solid shaft, the theta 2, okay? So here with the T is not given, so we substitute the values of L, G, and J respectively for hollow shaft and solid shaft, okay? So from our drawing, okay, from our figure, the length is 2 meter, but I convert it into millimeter by multiplying 1000 mm over 1 meter, and then this is the formula for J for a hollow shaft. Okay, and this is the formula of J for for a solid shaft, okay? So pi over 32 d to the power of 4 minus small d to the power of 4, and then we have 83 times 10 to the power of 3, pi over 32 d to the power of 4 for solid shaft, okay? So we use everything, okay? We use these following terms, we substitute all the values, and then we equate it to 2.5 over pi over 180, okay? So I use inequality, okay? Less than or equal to 2.5 pi over 180, okay? So we get for this value, okay, for the hollow shaft, we get 3.22994.825 times 10 to the 9 t. And then for the solid shaft, I get 7.6669 23188 times 10 to the negative 90. Okay, I equate it to the value of your theta or the angle of twist. Okay, so I add these two, so I get this formula and equate it to 2.5 over 180. So what I get is a torque. That torque should be less than 4,198,000.043 Newton mm. And then I convert Newton mm into kilonewton meter. Okay, so 1,000 Newton is equivalent to 1 kilonewton, and 1,000 mm is equivalent to meter. So I divide this into 1 million. So I get T is less than or equal to 4.004 kilonewton meter. Okay, so we have three values of T. So here we have 10.44 kilonewton meter, we have 4.714 kilonewton meter, and then in this case we have 4.004 kilonewton meter. So we take the smallest value of T. So therefore the torque is equal to 4.004 kilonewton meter. Okay, so that is our example number 4. So again, we use another here we use okay, so we will have another example. Okay, so we'll have another example. So our next example is 3.39. Okay, so we jump into 3.39. Okay, so from the topic torsion of thin-walled tubes. Okay, so we have 3.39 here. Okay, so we solve this one. Okay, so this is the figure. Okay, so a torque of 800 Newton Newton meter is applied to a tube with a rectangular cross section shown in the figure. Determine the smallest allowable constant wall thickness T if the shear stress is not to exceed 90 megapascals. Okay, so we'll try. Okay, so we have a rectangular section, cross section with 80 mm by 30 mm torque cross section for 3.39. So here is the solution. Okay, so this is now the solution. Okay, so what we are going to determine is determine the smallest allowable constant wall thickness. Okay, so we have the formula equivalent. This is Q. Okay, Q is equivalent to T over 2A sub O. Okay, so we know A sub O is the area. Okay, so this measurement 80 mm is actually from at the middle. Okay, this is not outside or inside. We are not using outside dimension or inside dimension. What we use is an average of the two, or at the middle. Okay, so we use at the middle of this one. Okay, so we have 80 by 30 multiplied by 30 mm, we got 2,400 mm squared. Okay, speaking of Q, we compute the shear flow by this formula to IT over 2AO. Okay, so I convert this 800 Newton meter into Newton mm by multiplying 1,000 mm over 1 meter. Okay, so that it will have a uniform value for uniform value for the length. Okay, so we substitute. So we have computed the value of Q, or the shear flow, by 166.667 Newton mm. And then we have the formula. Shear stress is equivalent to the shear flow divided by the thickness. Okay, so we all know that it should not exceed, okay, from the problem, it should not exceed 90 megapascal. And then, so from this equation, we will get the uniform thickness. Okay, so the uniform thickness computed is 1.852 mm. So that is the answer. So this is the problem, and this is the solution. Okay, so we will have another example. So after 3.39, we'll concentrate at 3.40. Okay, so this is 3.4, the figure for 3.40. So the constant wall thickness of tube with elliptical cross-section shown is 0.12 inch. What torque will cause a stress of 6,000 psi? Okay, so from that, okay, so we have this solution. Okay, so the constant wall thickness of a tube with elliptical cross-section shown is 0.12 inch. What torque will cause a shear stress of 6,000 psi? Okay, so given that torque as 6,000 psi, which is equivalent to 6,000 pounds per square inch, or 6,000 libra per square inch. So we have this formula. The shear stress is equivalent to the shear flow divided by the T. Okay, so by using that, we could compute the value of your shear flow. 6,000 libra, or 6,000 pounds per square inch, is equivalent to Q over 0.12 inch, okay, which is the thickness. So from that, we computed Q is 720 libra per square inch. And we all know, we all have that formula for Q also, which is equivalent to that torque divided by twice the area. Okay, so since the area of an ellipse is pi AB, so obviously from this figure, your A is the okay, 1/2 of 6, or the longer radius, so 3. And then we have the value of B, which is the shorter radius, so which is 1.5 inch. So we multiply that one. So okay, so Q is equal to 2AO, and AO is pi times 3 times 1.5. Okay, so we substitute from AO. Pi times 3 inch by 1.5 inch is equivalent to 720 libra inch, the shear flow. So we will have computed the value of T as 20,357.520 libra inch. Okay, so since our solution, the length that we used is inch, so from here we have computed your T as 20,357.520 libra inch. Okay, so we convert it into libra foot by dividing it by 12, since 1 feet is equal to 12 inch. So we get the torsion value is equivalent to 1,696.460 libra foot. So this is the problem, and these are the solution. Okay, and these are the solution. Okay, problem, sorry, my cell phone fall down. Okay, so I hope you understand our examples. Thank you.